Hello. Today, I'll be talking about the topics of cybersecurity and developing next generation vehicles. My name is Jun Kaguchi, Secure Flash Memory Marketing for Winbond. Modern vehicles can contain 100 or more processors or microcontrollers, and they're housed in ECU or electronic control modules located throughout the vehicle. These ECUs are typically connected in some form of network configuration. Conventionally, it can be over CAN bus or on a higher speed networking. It could be on an Ethernet. In any case, these modules will be talking to control units and to the rest of the vehicle. These processors each run software, and typically the code is stored in flash memory. Flash memory is used for ease of updates to address bug fixes, features, and performance enhancements. In a software-defined vehicle architecture, optional product features are enabled, and the flash memory may store the enabled feature configurations. Flash memory may be updated in person, for example, when a vehicle is brought into the dealership for service, or it may be over-the-air update to remotely configure an update. Future vehicles may consolidate these processors to a handful of very high-performing computing elements for a more effective software execution of advanced features such as autonomous driving, driving assistance, and other advanced capabilities. When over 100 controllers are connected together, it is critical that each component operate reliably. A failure of one can cause cascading effect that can result in safety situation. On an EE or electronic architecture vehicles, many critical operations are computer controlled, and a proper operation is critical to maintain a vehicle safety. To process so many systems, the computing elements are becoming far more complex and high performing. More importantly, the software that drives these systems are also becoming very complex, yet required to operate at the highest safety level. Now let's take a look at some potential situations regarding automotive cybersecurity. As vehicles on the road become more complex and reliant on advanced software and processors that run them, more incidences have been reported. Cars have operated in an unintended manner, including accelerating suddenly, stopping unintended, and perhaps electronic power steering have steered the vehicle against the driver inputs. There are reports where autonomous driving system didn't recognize pedestrians where they should have, or ran into other vehicles because they didn't recognize it. As tragic as these events are, from software perspective, it is another software bug that needs to be fixed. In software development, most imaginable situation is simulated and prepared for, but it is never perfect and not possible to prepare for every conceivable situation, especially when the number of these vehicles increase on the road. So a corner case where the situation is not anticipated could happen, and the software may or may not respond as it should. Currently, there is no real universal metric to gauge the software quality. Of course, they operate reliably in the simulated environment, but while some vehicles may have millions of test hours, other vehicles may have significantly less testing. So it is not possible for end user to know which solution is better tested, making them a beta tester for the lesser vehicles. Not only is it difficult to compare better vehicle software to those that are not, there's no real minimum bar to say that the vehicle is safe enough, so it is still driver's responsibility to operate the car, not the software. Now let's take a look at the software vulnerabilities. Much as in mobile phone software, automotive software periodically gets updated to fix software bugs or make performance improvements. If there are security holes found, then a software update will close that vulnerability. And like mobile phone software, it may be possible to downgrade the software version, exploiting security vulnerabilities and causing damage or operate differently. One such example is to brick any of the ECU modules by attempting to software update but fail to complete successfully. Perhaps a more malicious example is to rewrite the software so that the external user will take over and control the modules. You could never be sure that your vehicle is compromised. Perhaps the malicious software remains dormant until some trigger event. These cyber attacks are happening everywhere and all the time. Personal computers have been known to be infected with ransomware, malware, and other software that user did not intended. And consider that the software cyber attacks does not target individual systems, but a coordinated mass attack to take down in much larger scale. These incidences have happened and are happening more frequently. But why does it happen? In many cases, there are profit motives by the adversaries, either direct or indirect. From their perspective, it is a lot of effort and risk to penetrate these systems, so it better be worth their effort. So what are some situations of vehicle system being compromised? A relatively simple and a crude attack example might be to program an unauthorized spare key. It is possible to plug in a cloning device to a car, program a blank key to the car, and drive away. In a more peaceful example, a user might be able to program the engine control for more performance, economy, or both. These incidences have taken place for a very long time, as a spec for automotive network has been public for some time. In a more modern and complex cyber attack, consider that an adversary may pretend to be the vehicle manufacturer and perform massive over-the-air update to all the cars, all at once. A vehicle may not be able to tell the good update from the bad ones, so if such attack is successful, a massive shutdown might take place. Fortunately, such incidences have not happened yet, but there's no guarantee that it will never happen. After all, over-the-air update is a built-in feature for these cars. To understand why these cyber attacks can happen, we need to consider the flash memory that store code updates can be easily programmed. These devices are designed to be programmed and store the new code, obviously, but like a door with no lock, anyone can program it. There are various software mechanisms that are designed to prevent malicious programming, but that is like putting different barriers to reach the lockless door. The flash memory is still programmable. With conventional flash memories, it will still be an endless security updates patch to close one vulnerability after another. So is there a way to put a lock on the door itself? By incorporating security function in hardware, a much higher level of security can be achieved. This is how the chip on those credit card operates, for example. Only the authorized user can access or program the content of the chip. For automotive or embedded application, flash memory with secure hardware can be used to achieve the same result. Only the authorized user with proper credentials can access the memory. This will be the lock on your door. We discussed about cyber attacks so far. Now we will look at supply chain security. In looking at hardware security at the component level, you have to be certain that all devices on the system need to be genuine and trusted. Much is known about fake or counterfeit chips that is in circulation. In many instances, fake chips are developed to be cheaper substitute to the authentic devices with low performance, less reliability, and with little or no testing. The motives are direct economic benefit to use lesser devices. But in a more malicious situation, a component can be designed to operate differently than intended. They may lurk in hiding, operating as expected until some trigger event. The malicious device may be interjected during transit in handling by unauthorized entities between the trusted factory and manufacturer receiving it. In the case of malicious software, the unauthorized programming services may be programming the device with malicious code. A challenge of supply chain security is that once interjected, it is very difficult, nearly impossible to find out if the device is compromised. You will need to ensure that the electronic components are always in trusted hands once it leaves the trusted factory. From an adversary perspective, a successful interjection may be complex, expensive, and time-consuming. You may set up an entire supply chain ecosystem just to penetrate the target. But if the target and result is worth investment, adversaries will be willing to make that investment. With so much potential risk to general public and automotive market, are there any rules and regulations to protect us? There are some efforts put into place. One such example is ISO 21434 standard. It defines cybersecurity engineering standards, guidelines to protect vehicles and users. It is in effect from July 2024, and any new vehicles on market after this date need to comply to the standard. This is a major step forward for automotive cybersecurity because prior to the standard, there was effectively no consistent regulations. Automotive electronic components also have functional safety standard, the ISO 26262, that defines different level of functional safety. This allows for application of consistent standards in developing reliable vehicles. But why are these regulations needed? If the car runs and operates, isn't that good enough? Actually, as vehicles are expensive, potentially dangerous products sold in large numbers, a consistent and universal safety rule is needed to ensure public safety. Otherwise, it is difficult to determine if a vehicle is designed with safety in mind or cost saving in mind. By setting these rules, all manufacturers must meet this minimum level of safety requirement. This allows for honest manufacturers to develop a good product without a concern for other vendors trying to undercut by taking safety shortcuts. So what are the measures that automotive designers can take to ensure safety and security? In ensuring supply chain security, manufacturers can look at suppliers with safety certifications from reputable certification organizations. They will evaluate suppliers' manufacturing processes to ensure high-level security processes, make actual site audits to validate it, and provide their approvals. This can affect both the manufacturer themselves and any post processes, including device assembly and programming services. Even the transportation services are subject to evaluation to ensure that no detours or side stops to compromise integrity are possible. In addition to working with reputable certified suppliers, a hardened security devices will give that lock on your software storage. This ensures that the electronic components arrive to factory in a safe and secure manner and will ensure any operations once in the field will be trusted. Winbond offers advanced secure flash memory solutions for automotive markets. It is designed and offered in industry standard packages for drop-in substitutions to conventional flash memory. The security mechanism is certified by multiple security certification standards, and its encryption strength is among the toughest. It is designed to counteract many attack modes, including authentication, anti-rollback, and resiliency capability that gives robust protection against attacks. It is designed to meet automotive qualification requirements. In summary, we want to emphasize that the manufacturers need to independently ensure your supply chain security. Don't trust this key security element to others. Be aware that the regulation is the minimum bar to clear. As an insurance, you can take the minimum insurance for low value, but consider a robust solution to protect your interests. As attack modes change and improve over time, the regulations that protect it will evolve over time as well. Just going for the minimum coverage may end up being insufficient and non-compliant in the future, much less expose you to a higher risk. For the most reliable and trusted solution, consider to incorporate secure hardened flash memory as your cold storage device. So here I will list out answers for some common questions regarding the topic. There are several business use case and product benefits for software-defined vehicles. First, SDV means that each vehicle is fully equipped and capable, but functions may be disabled depending on user options. This simplifies vehicle production as it reduces different product configurations, and every vehicle is fully loaded. From business aspect, this allows manufacturers to sell a vehicle feature independently or as a package, either as a single sale or as a subscription. Financially speaking, this will be a very high margin sale of features. This benefits consumers as they will pay for product and functions they only want and need. The vehicle will be future-proof as it will build in many available capabilities to meet the needs for today and in the future. There are downsides to SDV, in particular in EV configuration. The product reliability is expected to be higher for EV compared to internal combustion cars. Therefore, service needs can be reduced. As many updates will be done in over-the-air update than a physical module replacement, users may find less need to visit the dealership or repair facility. So generally, this is not a good news for mechanics. In terms of the increased security concerns, the SDV will increase software complexity significantly. Users will experience many advanced features, including better driver assistance feature, which can improve over time, and new services in the future. Keeping these software updated at all times require frequent over-the-air updates. The update process, similar to those on mobile phones, can make a system vulnerable. Although there are many fail-safe measures, there is a risk of update failing and possibly breaking the system. This can happen by accident or by malicious adversaries. With EE architecture, most drivetrain components are computer and software controlled, including steering, acceleration, and braking. If a vehicle starts to operate erratically because of wrong software, accidents can happen, and at the worst case, in a massive scale. In terms of the motivation for adversaries, compromising the vehicle software is a complex and time-consuming task, so it needs to be worth it for the adversaries. They can hijack the vehicle as a ransomware, or enable features without paying for it, or in a traditional business of just stealing the car. A large-scale attack can cause significant disturbance, in which may be state-sponsored type attacks. In particular, concern is that there is no currently consistent and strong enough cybersecurity regulations. One vendor may have a very robust and costly implementation, while a lesser vendor may do just the bare minimum. Automotive manufacturers have known to go the lesser route, for example, to ship vehicles without immobilizer when it was not mandated, even though there was a threat and it was a standard practice by almost everybody else. Adversaries will look for these lesser vendors, knowing that they will do just the minimum. In terms of cost, as just mentioned, you can go as cheap as possible, paying nearly zero as long as it meets the checkbox requirements. But as an insurance coverage, you don't need it until you do. Manufacturers with a reputation to protect will likely invest more, while a lesser manufacturer only has a low price as a selling point. And as an insurance, that one day you will need it and may realize you made the wrong decision. In the overall scheme, strong cybersecurity protection is not a high cost, but from a manufacturer perspective, every penny not spent is a penny in profit. In terms of the consequence for insufficient cybersecurity measures, consider that a PC user can see that they're always under attack from computer virus, malware, and other harmful software. This is why most computers have some form of antivirus software protected. Imagine back when computer virus was unknown and computers were unprotected. So vehicle software is somewhat in this stage, but protection will be needed because adversaries will be there to attack the vehicle software. But unlike PCs where end users have their choice of antivirus to install, for the vehicle software, you must rely on the manufacturers to make the adequate protection. Finally, the reasons against implementing. So as with antivirus software on a PC, which is yet another piece of software running on your computer, automotive cybersecurity is yet another component which increases system complexity. So a well-designed system is needed to perform well. A poorly designed security solution may be worse than without it. Owners of newer vehicles may have experienced that software glitches on your infotainment system once in a while. Adversaries will find these kind of security glitches and find ways to exploit them. But for most users, you will not operate a PC without an antivirus software, operate your mobile phone without the latest security update, and for the same reason, you will need a robust automotive cybersecurity implementation.